Welcome to Metal Casting Lecture Series by Professor Joyjeet Ghose. This is the 7th lecture of a series of lectures. This lecture will be on molding sand testing methods. He will be discussing about various types of molding sand test like grain fineness test, hardness test, permeability test, strength test. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture 7 on different types of molding sand testing. Now, very often in a foundry we have to test the sand and understand and determine the properties of the molding sand that we'll be using for the casting processes. So therefore we can carry out various types of tests on the molding sand. Some of the tests are grain fineness test, where we determine the grain fineness number, which indicates how fine the grains are. As you know, finer grains will give better surface finish but lesser permeability, and coarser grain will give better permeability but rough surface. So therefore it is very important for us to determine the fineness of the grains that will be sand grains that we'll be using for our casting. Then we can determine the amount of clay content, we can determine the amount of moisture content, we can determine the permeability of the molding sand, we can determine the hardness of the molding sand, we can determine the strength of the molding sand. So various types of tests can be carried out to find out the properties that is of the molding sand we are using. So some of the tests we will be discussing, not all the tests we will be discussing here. We'll start with the grain fineness test. So in order to measure the grain fineness number, we carry out this test, and this is done by a machine called sieve shaking machine. So as the name suggests, there are a number of sieves placed vertically, one on top of other, like this. The sieves are placed on top of each other and these sieves are of different mesh sizes. So the open or more open sieves are placed on the top and the finest sieve is placed at the bottom. So finer sand will collect at the bottom or the pans on the lower side, and the rough sands or the coarse sands will be collected on the pan on the upper side. So like that, in this machine there are pans, and these pans are shaken. As the name suggests, sieve shaking machine, there is a motor which vibrates the pan, and what we do is that we first wash the sand that we are will be measuring the fineness. We wash it because we want to remove any kind of clay and other foreign materials in it, and we dry it. The sand has to be dried. So this dried sand is placed, measured, weighed, and we note down the weight, total weight of the sand that we are going to place it on the top pan, on the top sieve. On the top sieve, we placed a measured quantity, weighted quantity of the dry sand, and then we start the machine for a predetermined period of time, for a certain period of time, and then sands of different sizes will be segregated into different pans, and then we collect or remove the pan and weigh the amount of sand in each of this pan, and there is a formula, there is a multiplying factor. We multiply the percentage of weight retained in each of the pan with the multiplying factor of that particular pan, and then we sum it and we divide it by the 100%. That will give us the sieve shaking or the grain fineness number. So the grain size is determined by the grain fineness number. It can be tested with the help of equipment called sieve shaking machine, and it consists of sets of sieves varying from 6 to 270. So the sieve with minimum mass number has the largest aperture and it is placed on the top. it is like this. There's stainless steel sieves here. You can see the finer mesh and the more open mesh here. So entire thing is placed here. There is a motor which vibrates it for a certain period of time. Then these pans are removed and we take it out and we pour the sand in each of this pan and we weigh it and we note down the weight of each of the quantity of sand retained in each of the pans, and we note it down and then find out the percentage of that sand retained, likewise for each pan, and then we calculate it. So the procedure is basically simple. Sand has to be washed to remove any kind of clay, and it is dried, and then we weigh the sand, the amount of sand that we want to test. We weigh it and then pour it, place it on the top sieve, and the entire unit is shaken or vibrated for a definite period of time, and the sands fall through, and the sands will be segregated based on the size. So the finest sand will be collected at the bottom pan, and the coarser sand will be collected on the pans on the top side. So we'll take out the pans and we'll measure the quantity of sand retained in each of this pan and note it down. So after noting it down, so there is a multiplying factor for each pan. We're multiplying it by the percentage of sand retained, and then we'll find out the summation of it, and we divide it by the total percentage, 100%, and that gives us the grain fineness number. So American Foundry Society has the multiplying factor like this. We have from 6 to 270, and the final pan, which do not have any kind of sieves. So finest grains will be collected here, and will multiplying factor of 300. Okay. So this is an example I have taken from P. N. Rao book, where he has given that the sand poured is collected in sieve number 40, 50, 70, 100 and 140, and the multiplying factor of each of these is given here. You can see 40 is 30, so 40 sieve number is 30 here, and 100 is 70, 100 is 70. So, and the percentage, this is the gram retained, so in terms of percent, it is given as 5, 28, 48, 14 and 5. So this is the total. So if you can, 2.459 of 50% will be 5% here, like that. So total percent is 100%, and you multiply this with this will be 150. 28 into 40 will be 1120. Like that we calculate this thing. So this will be in the numerator, 5150 divided by 100% will give you 50.5, 51.5. So this is an average fineness of the grain. So normally we go for this average type of grain fineness number. So higher will give you finer sand, but however the permeability will decrease. Okay. So hardness test, like any hardness test, mineral hardness test or local hardness test, we measure the indentation of the sand. So for measuring the indentation of a sand, there is spring loaded equipment with a spring loaded ball. So when you click on that switch, the spring loaded ball will move out under the spring pressure and make an indent on the sand specimen. By measuring the dimensions of the indentation, we can, by using a formula, we can measure how hard the sand is. So in this manner, we can measure the hardness of the sand. I don't have a picture of it, but in the internet, if you search hardness tester for sand hardness tester, you'll find the simple equipment is there. You take it in front of the sand and push the button. This ball will move down and create an indent and measure the dimension of the indent, and using a formula, you can find out the hardness number. Then we have permeability. It is very important for us to know the permeability of the sand. Our sand should be permeable enough so to allow the gases to escape. So here what we have is basically there is a bell jar and a jar. This jar is fitted or balanced on a jar containing water. So this volume of this bell jar is 2000 cc. So it is assumed that the bell jar has 2000 cc of air. So this is connected to a tank or a jar in which we fit this specimen. The specimen is of very standard dimension, 5.08 centimeter diameter and height 5.08 centimeter height. Okay, and this is the seal. This is a seal, mercury seal, and the pressure we can measure using a manometer or pressure gauge, whatever it is. We can measure the pressure. We keep it to atmospheric pressure. Now when you start the valve, open this valve, the air from here will come down and will flow through this test specimen. This is the test specimen. This is the test specimen. We use a mold to create this test specimen. There is a mold. If you buy a permeability tester machine, then you will be given a mold. In that mold, you make a specimen. The specimen is of 5.08 centimeter diameter and height 5.08 centimeter. So that specimen is fitted here, and the bell jar, as you switch on this valve, open this valve, the air will come down and the jar will also come down. So this jar will reach here. So when it reaches here, what happens? 2000 cc of air is made to pass. So we know the amount of volume of air that is made to pass, that's 2000 cc, and we will note down the time the bell jar reaches this portion. So that means we can assume that in time noted, 2000 cc of air is passed through this jar, through this specimen, So in this manner, using a formula, you can measure the permeability number. So what we measure is basically measure the time that is required to pass 2000 cc of air through a specimen, and the size of the specimen is 5.08 centimeter diameter and the height is 5.08. Okay, so using this we can measure the permeability of the sand. So this is the formula that we'll be using. So V is volume of air, V into H. H is the height of the sand specimen, that is 5.08, and P is the pressure. The pressure is air pressure, which is, let's say, take it around 10 gram per centimeter square, and A is the cross-section area of the specimen, which is pi by 4 d square, that is pi by 4, 5.08 square will give you 20.268 square centimeter. Time in minutes, remember this time is in this formula, it is in minutes. So we measure the time that is required. So the formula ultimately becomes 2000 into 5.08 centimeter divided by 10. Okay, divided by 10 divided by this 20.268 by time in minutes will give you 50.128 by time in minutes divided by this into 60 will time in seconds. So this is the formula that is used to calculate the permeability number. One more test that we'll be discussing is the strength test. It's a very important one. Identifying the strength, basically the green strength. So in green strength, basically the content the moisture. We prepare a specimen of the sand, and that specimen is fitted between two jaws, and this jaw can be interchangeable. You can fit various types of jaws like this flat plated, jaws like this shape, and jaws like clamp for tensile test, for compression test, for shear test. So you can change this, and we apply the hand pressure here by a hand wheel, rotating hand wheel, and we can, the amount of pressure that is required before fracturing we can measure, or before breaking of the sand we can measure. We move it inside for compression test, we take for tensile test, we take it out, and we can measure the tensile stress. So all these tests can be done on sand. So in this lecture we have discussed the different types of tests, yet we have not discussed here is the test to determine the clay content and test to determine the moisture content. Rest all the tests we have discussed. In the next lecture we will be discussing about cores and core making. Thank you for patiently hearing. If you have any doubt, please feel free to contact me. Thank you.